We start on chapter 12. This is the last chapter for this week, and exam number 4 is going to be chapters 10, 11, and 12. Okay, now in this chapter, we are going to introduce gravity with all the aspects related to it. We will study Newton's law of universal gravitation. We will study the gravitational attraction when we have spherical bodies. We are going to also verify Kepler's laws of orbital motion, first and second and third. We will see how we are going to modify the gravitational potential energy function. And finally, we will work with energy conservations and talk a little bit about tides. Now, there is something very special about Newton, that he made the gravitation universal. Maybe before we were thinking of, okay, just we have that gravitation force between the astronomical objects like the earth and the sun, the moon and the earth and all the stuff in there. But Newton was able to say that this is really universal, then everything is going to follow the same. Now, I will say, like here, of course, there we know that the force of gravity is being exerted on objects that they are on the earth. What is the origin of that force? And Newton's was able to say that the force must come from, of course, the earth as an object. And then again, he concluded that it's the same force that is going to keep the moon in its orbit. Now, we know here that the same way that you are attracted to the earth is attracted to you. Then I will say we have here, okay, in Newton's third law forces, where this is force from the earth on you, and you will apply a force from you on the earth. They are in Newton's third law pair, and they are equal in magnitude, opposite in direction. When there is such a disparity in masses, the reaction force is undetectable, but for bodies more equal in masses, it can be significant. And we're going to see that this is really the thing that, like, when the masses are really small, okay, maybe this force will not that significant. And the reason is the value of this G, which is really a very small value. Okay, it is 10 to minus 11 in Newton's meters squared per kilogram squared. And this is what is making this force the weakest force in nature. Now also, as I mentioned before, Newton was able to find that force has to do with the masses. Also, by observing things, he was able to conclude that also must decrease, the force must decrease as the inverse of the square of the distance between the masses. And this is the reason why we call this formula inverse square law. Then we call this inverse square law. And G, as I mentioned, it is the universal gravitational constant, which is really a very small value. Now, also Newton's added his insights here And he said the force accelerating an apple downward is the same force that keeps the moon in its orbit, which is the gravitational force. Then the gravitational force, it is something universal, and we added that value like universal gravitational constant, the 6.617 10 to minus 11. As a conclusion of all these information and observation, every particle in the universe attracts every other particle with a force that is proportional to the product of their masses. This is the reason why we, if we are in the setting of a classroom, we will not feel that attraction between us. The reason is that the product of our masses, as small masses, is not going to be significant. And it is inversely proportional to the square of the distance between them. And this force is acting between, like acts along the line that is joining the two particles. And remember, these two forces are action-reaction pair. G is very small number. This means that the force of gravity is negligible unless there is a very large mass involved, such as the mass of the Earth, the mass of the Sun, or the mass of like any of these astronomical objects. Which is stronger, Earth pull on the Moon or the Moon's pull on the Earth? Of course, they are both equal because we said these forces are in Newton's third law. Then the forces are equal in magnitude, opposite in direction. Now, if the distance to the moon were doubled, then the force of attraction between the Earth and the moon would be, and here just I want to show you how we're going to conclude this, because this is a general question. If I will say, like, of course, this was the mass of, let's say, the Earth, and this is the mass of the moon. Okay, and this is R, which is the distance between their centers. If I am looking at the new force now, then this is mass of the Earth, mass of the moon, and now we said like the distance was doubled, and this is 2R squared, and then F prime is going to be 1/4 of G mass of the Earth, mass of the moon over R squared, and that is 1/4 of the initial force. This is how you are going to deal with situation when I will say maybe rank forces according to maybe like from greatest to smallest, or like from smallest to greatest, depending on information given to you, like the relation between, let's say, the radii and the masses. If an object is being acted upon by several different gravitational forces, then the net force on the vector sum of the individual forces, and this is called the principle of superposition. And we did this is also, it's not something new. The net force, you're going to add all the forces acting on the object, then you might have a situation where you are going to have two masses, and maybe there is a third, let's say, mass that is pulling the one in the middle, and then you might subtract the forces, you might add, you might but it's gonna be vector addition. You might have these three objects sitting in a setting of like a triangle or a square or a rectangle or what. Okay, then this is not new. Now, here we have a planet that has a mass m, is at a distance d from the Earth. This is the Earth here, and this is m. And another planet that has 2m, and it is sitting at a distance 2d. Which force vector best represents the direction of the total gravitational force? Here you need to know that first, when I compare force 1 with force 2, the force to the due here to M is going to pull the earth with F1, and here due to 2M is going to be 1/2 F1. All right. Now, of course, I can exclude E and A because my resultant should be something like this. Okay, but also more information. C is not, because C will represent when the two forces are equal. Now, D also, it's not correct because it will, D will be the resultant if that force here, if this force is going to be more. But we know that this force, like the force due to M, is more, than B is the correct answer. Okay, now I will say, like, sometimes it's going to be difficult for you to make this kind of argument. You can have numbers and you can solve it, but just first you need to know what is the relation between the two forces, which force is more than the other. Now we're gonna try it here. When the earth, moon, and sun form a right triangle with the moon located at the right angle as shown in the figure below, the moon is approaching its third quarter. The earth is viewed here from above its north pole. Find the magnitude and direction of the net force exerted by the moon. Give the direction relative to the line connecting the moon and the sun. Exerted on the moon, not by the moon, sorry. Now, this is the equation for the force from the sun on the moon, and it is in this direction. And the other force, it is from the earth on the moon, and this is its direction. I plugged in here my numbers. Okay, like the distances between the sun and the moon, and the mass of the sun, the mass of the moon, and also for the earth I did the same thing. I have calculated the forces here, and then I know that they are at 90 degrees. Then I will say this is gonna be FSM squared plus F moon earth squared, and the answer is 4.79 10 to 20 newtons. And I can also calculate the angle, which is 24.4 towards the earth of the sun moon line. Now, we know that if I have a spherical object, then the gravitational force between a point mass and the sphere is going to be the force as if all the mass is concentrated at its center. Okay, then, and we're going to do that approximation. What about the gravitational force on objects at the surface of the earth? The center of the earth is 1 earth radius away. So this is the distance that we are going to use. Then this is the force that we are going to use. And the acceleration is going to be A, G, mass of the earth divided by R squared. And this is how we calculated that the acceleration due gravity is going to be 9.81. By the way, this, I will say this relation, okay, then I will call it G. G of any planet is going to be that capital G, mass of that planet divided by R of that planet. Okay? And again here, you might be given the, I will say, the relation. Let's say we have a planet that have double the mass of the Earth, and let's say 3 times the radius of the Earth. This means that this is going to be 2 over 9 and this is G ME over RE squared, and that is 9.81. Okay, and then this is how you are going to calculate the acceleration due gravity on any planet. Now, also, we can say that what if I have an object that is really very far from the surface of the Earth, then my force, I should add that h here, and my acceleration now is going to change. Then if you are at the top of Mountain Everest, which is 8,850 meters up, you find that A is going to be less. Okay, why less? It is more altitude, 9.78. And if we have a satellite that is 8 × 10⁶ is going to be, the acceleration of gravity is going to be 1.916 meters per second squared. Then that gravitational field is affected by the distance. Then if you are high in the sky, or like high in the universe, like above the Earth's surface, you're going to get different values. We will find that also that the acceleration due gravity decreases slowly with altitude, as you can see here. Now, once the altitude becomes comparable to the radius of the Earth, the decrease in the acceleration of gravity is much larger. Okay, and here we are showing you kind of, I will say, a graph that is going to show the values of acceleration of gravity with respect to the height, and this is in miles. One of the things that I want to maybe mention here, it is that the geosynchronous satellites are the ones that they have the same period as the Earth rotation, and they're gonna spot the same, they will be on the same spot the whole time because it is synchronized with the rotation of the Earth. Now, you weigh yourself on a scale inside an airplane that is flying with constant speed at an altitude of 20,000 feet. How does your measured weight in the airplane compare with your weight as measured on the surface of the Earth? Of course, you are away from the Earth, and you have an altitude added to the radius of the Earth. When we are going to calculate G, which is the acceleration due gravity, then your weight is going to be less than your actual weight. Now, I will say the radius or the height is not the only thing that can vary. Sometimes we have variations of mass. For example, you could have very dense rocks below you. This would give a greater local mass because gravity also depends on that density of the mass. Like the mass is going to be a factor. These small variations can be measured and used to find mineral, high density, and oil, low density deposits inside the Earth. All right. Here we have a science fiction tale describes an artificial planet in the form of a band completely encircling a sun, with the inhabitants living on the inside surface of where it is always noon. Imagine the sun is exactly like our own, that the distance to the band is the same as the Earth-Sun distance to make the climate temperature, and that the ring rotates quickly enough to produce an apparent gravity, the one that is G on the Earth. What will be the period of the revolution of this planet's year in Earth days? Okay, first, of course, I need maybe to derive an equation. We know from the centripetal that A equals V squared over R, and the period is the total distance 2 pi R divided by V. Also, we know that F equals gm, mass of the object, times mass of, let's say, the sun, divided by r squared equals mg. And from that, we will be able to find a relation that is going to give us the period. Okay, and finally, I can find the period as this. This is all my derivation. And finally, this is the one that I'm going to use, where I have t squared is going to be measured and calculated as 4 pi squared times r cubed divided by gr squared. And I did calculate this in seconds, of course. And then finally, you can convert this into days, and it's going to be 9 days. I'm gonna stop here for the